A very good afternoon from India. I'm located in Kolkata, eastern part of India. And thank you, Michael and Azam, for this nice introduction. And I would like to thank Deposit Hubs for this invitation to present this deep dive seminar. I will talk about origin of Indian Archean chromite deposits. You know that India is an important supplier of chromium resources for a very long time. And if you see the statistics from 2020, we are supplying near about 10% of global production of chromium resources, which are going to industry. So these deposits are very important. Most of our chromite deposits are restricted in Mesoarchean period, where we have chromite deposits posted within some Mesoarchean to early Archean to Mesoarchean greenstone terrain. So we know that mesochromite deposits are genetically related to ultramafic magmatism that are restricted to specific periods of time and have specific tectonic settings. So we are talking about ultramafic magmatism in different time period. So if you see this particular plot by Clive Stowe, published in Economic Geology in 1994, you see that most of the phylitic hosted deposits are restricted in Phanerozoic. We have huge amount of chromium resources that are restricted in Proterozoic era, when we have large igneous provinces, and those large ultramafic large igneous provinces, they host sterniform chromite deposits. And we have some early Archean to Mesoarchean chromite resources within the high-grade terrain, as well as in the low-grade greenstone belt. This is the important chromite. This is the geographical distribution of important chromite deposits, and you can see that most of the important deposits are basically located at the southern part of the African continent. We have Bushveld complex and Red Dyke, and there are some other type of deposits in Zimbabwe, which are located within the Seleucid greenstone belt. Then we have the Stillwater complex in North America. We have Muskox lead intrusion in Canada. All are large chromite producing deposits. Then all these ophiolitic hosted chromite deposits most of them are located within the Alpine Himalayan belt, along the Alpine Himalayan belt. And Indian chromite deposits are located in the Odisha state, the eastern part of India. This is the production data of chromium resources based on USGS mineral commodities 2020. And these productions are in terms of million metric tons. Here we can see that India was producing 4.1 million metric tons, whereas South Africa was producing 17 million metric tons. And we have big deposits in Turkey, Kazakhstan, and Finland. So together, and along with other countries, the world was producing 44 million metric tons of chromium resources. And you can see the contribution from Indian deposits. It is more or less 9 to 10% actually. So in a chromite deposit, chromite is the only primary source of chromium. It records the overall process of concentration by magmatic crystallization. And we can use primary composition of chromite as a petrogenetic indicator. The reason is that chromite starts crystallizing from a very early stage of magmatic history of an ultramafic magma, where it crystallizes along with olivine and other pyromagnesian silicates, and it continues for a while. And that's why in an ultramafic sequence, we can get say chromite at the lower part, chromite at the upper part of that ultramafic sequence as well. So we can analyze those primary composition of chromite along with the coexisting olivine or other ferromagnesian silicates, and together they can give some valuable petrological information of as well as the evolution of the coexisting parental magma. So uh, we can use this composition as a petrogenetic indicator to understand the evolution of the polyigneous complex. They are marketed according to users under three categories. One is metallurgical ore, so where Cr2 should be more than 40%. We have chemical ore, where Cr2 should be 42%, more than 42%. We have refractory ore, where Cr2 plus Al2 should be more than 60%, and Al2 is a very important component where it should be more than 20%. However, SiO2 should be less than 10%. They have mentioned about SiO2. The reason is that in industry or in mining districts, they are basically, the miner people, they are basically analyzing bulk chromitite ore. And you know that chromitite has interstitial silicates, so there should be some SiO2, but their concentration should not be more than 10% if we want to use them as a refractory. And another thing is that chromitite is very important. The reason is that chromitite hosts platinum group element deposits, and one of such is the UGT chromitite layer in the Bushveld complex, which is the largest platinum group element resources in our planet. So depending on the forms and textures, TP Thayer in 1960 classified chromite deposits as styrofoam deposits or podiform deposits. Styrofoam deposits are coming from layer intrusion. Podiform deposits are coming from upper mantle part of the ophiolitic complex. In 1994, Clive Choi classified chromite deposits based on geological settings, which is more simplified and more appropriate, I think. It is one type is Bushveld type chromite deposits, which are basically intercontinental reef-related layered intrusions hosted chromite deposits. Ideal example is the Bushveld complex or Stillwater complex or Mascot's layered intrusion or wet dike. And another variety is ophiolite hosted chromite deposits, where we have at the upper part of the ophiolitic sequence, upper mantle part of the ophiolitic sequence, we have pot-shaped, elliptical shaped, highly discordant, concordant chromitite, massive chromitite bodies. At the same time, we have styrofoam chromitites at the lower part of the crustal magma chamber of ophiolitic sequence, where those styrofoam chromitites are hosted within ultramafic cumulate rocks. So these are some field photographs. This is a nice chromitite layers interlayered with silicate rocks above and below. Here it is anorthosite, and below that we have norite, and up on this chromitite layer we have pyroxenite. This is the famous Dwarfs River section of the Bushveld complex, where we have spectacular layering of styrofoam chromitites interlayered with anorthosite and tites from the womanophyllite. These photographs are taken from Ahmed and Arai with their contributions to mineralogy petrology paper, and you can see the nature of this chromitite body. And sometimes in womanophyllite we have chromitites like dike or seal-like bodies. So they're highly discordant to concordant and elliptical eye-shaped. Different types of chromitites are present. But most important thing is that all these mantle-hosted, upper mantle-hosted podiform chromitites, they are characterized by occurrence of nodular chromitite. So these are the nodules of chromitites cemented by olivine. Now these are serpentinized. So there is a third type of chromite deposits which are occurring in which occur within the seal-like intrusions, mostly restricted in the low-grade greenstone terrain in the early Archean to Mesoarchean greenstone belts, popularly known as conduit type. They're less recognized, where we have both styrofoam and pot-shaped characters in the massive chromitite. They're highly deformed, dissected, and the host rocks altered, but cumulate textures are still preserved. In terms of chemical composition of chromite, they're characterized by higher Cia number and higher Mg number. Common example is Noamundi and Shukinda igneous complexes. Those are located in the Shingmung Craton, India, Eastern India. We have Nagihili Sargur Belt in the Western Harbour Craton, India, in the Bad River Seal, another example, and there are some similar kind of chromatites in the Survey, Zimbabwe, which are associated with the Seleucid Greenstone belt. If we discuss about the origin of stratiform chromatites, we know that this kind of stratiform chromatites is common in visual complex, in still water complex, like this is the G chromatite layer of still water complex. This one is famous Dwarf River section. And the mechanisms proposed to account for the origin of these chromatites that involves changes in chemical or physical conditions in the magma chamber. It causes the magma to become supersaturated in chromite, and it helps to remove other phases from the liquidus, and chromite becomes the only liquidus phase for a particular time period, and that helps to crystallize chromite as a monomineralic phase. And as a consequence of that, we can expect formation of a stratiform chromatite layer in the layer intrusion or crustal magma chamber of the porphyritic complex. And the proposed changes are increases in total pressure. Then we can change oxygen fugacity. We can have oxygen fugacity change in the magma chamber. Then this contamination model by Irvine in 1975, the activity of SiO2 can be changed. And as a consequence of that, we can have that stratiform chromatite layer. And however, most widely accepted mechanism is the magma mixing model by, as proposed by Neil Irvine in 1977. He rejected his earlier model, this contamination model, and proposed this particular model. And this model is very elegant model to describe and to explain the occurrence of stratiform chromatite layer, and formally based on field evidences and experimental work. This is the Mascot's layer intrusion where we have periodite, chromatite, then occurrence of orthoperoxenite. And Neil Irvine proposed that if we have a differentiated magma crystallizing olivine and chromite at B, at position B on the protected line of olivine and chromite, and there is another magma introduced in the magma chamber, extant magma chamber, the primitive magma A, composition A, and if A and B magma mixes, what will happen? A hybrid will form that will be within the chromite saturated field, and during cooling for a certain period of time, we can expect crystallization of chromite as the only liquidus phase, and as a consequence of that, formation of a stratiform chromatite layer. So this is a very nice mechanism to explain all this kind of repetitive occurrence of chromatite at the basal part of the cyclic unit in different layered intrusions and chromite deposits. And regarding origin of podiform chromatites, I should mention here that this pot-shaped chromatite bodies are surrounded by dunite. This is a dunite rim. This is a characteristic feature in omonophyllite and many ophylites. So they have dunite halo, and these are sitting within the mantle hydragite. So to explain this, Lago proposed in 1982, published in Journal of Petrology, that if any basaltic magma or exotic magma flows through the steeply inclined tensional fractures within the upper mantle, what will happen actually? It will react with the host Hadbargite, and it causes local melting of orthoperoxene in the surrounding Hadbargite and generates residual danite lining. And there will be a convection due to cooling down of the magma when it reaches here, and that convection convecting magma will meet primitive magma here, and we can expect magma mixing at the boundary zone. As a result of that, our chromite will become the only stable phase, and we can expect formation of this kind of chromatite body. So this model explains very nicely shape and discordant orientation of pores, dunite halo surrounding that particular podiform chromatite body, and a nodular texture of the ore through collision and coalescence of grains in convection circuit. And we can expect formation of that kind of nodules in this mixing zone, or the boundary region. So with that background, I would like to describe some of the Indian Archean chromites and their possible tectonic setting and origin. So we have a couple of ancient cratons in Indian Shield. This is the Shinghum Craton, then Dharwar Craton. We have Bhandara Craton or Bastar Craton. We have Bundelkhand Craton, and there are ancient zircons that has been reported from most of the cratons, and their weight is like 3.6 to 3.1. And in case of Shinghum, we have more than 4 billion years old xenocristic zircon. And within this, this is the geological map of Shinghum Craton, where these are the granitic basement rock, and these rocks are mostly early Archean to Mesoarchean in age, and these are surrounded by Mesoarchean to early Archean to Mesoarchean greenstone belts, where we have intercalated metavolcanics and metasediments. And within those metavolcanics, at the lower part of the metavolcanic sequence, we have chromatic basaltic rock, and at the lower part, we have accumulated dunite and pyrrhotite. Those are chromite bearing, and those chromites are extensively altered. And associated with these metavolcanic and metasedimentary greenstone belt rocks, we have this plutonic igneous complex, this black colored portions. We have Shukhinda complex, we have Noamundi complex, and we have Mayurbhaj complex. And Shukhinda is famous for its chromite resources. Noamundi has chromite as well as nickel copper sulfide and PG, and there is titanium and vanadium bearing magnetite deposit as well. In the Mayurbhaj igneous complex, we have titanium and vanadium bearing magnetite deposits that are hosted within the upper gabbro anorthositic rocks. So this is the geological map of Noamundi complex, where at the lower part of the complex, we have ultramafic unit. Within the central part of this ultramafic unit, 3 thick chromitite layers hosted within serpentinized dunite. At the western part, we have orthopyroxenite to hydrargite rock, and at the eastern part of this dunite, we have another orthopyroxenite unit. And in between the contact of this eastern orthopyroxenite unit and the lower part of the gabbroic rock, there is a breccia zone, and that breccia contains clasts and fragments of ultramafic and chromatites, which are PG rich, and sometimes the matrix of the these clasts and fragments are cemented by pegmatitic gabbro, and those pegmatitic gabbro also contains good amount of platinum group element mineralization. And at the upper part of the gabbroic unit, we have magnetite bodies, which is titaniferous vanadium bearing magnetite. And in a previous study, we have discovered PG mineralization within this magnetite ore bodies, where palladium concentration is higher than the other platinum group elements. Sometimes PG value is more than 3 ppm. And these are some of the field photographs from the Noamundi igneous complex. This is the westernmost massive chromitite unit, which is hosted within a dunite. This dunite is extensively serpentinized. At the middle part, we have another 2 chromitite ore bodies. One is here, and another one is this side, followed by a dunite unit. And the character of the chromatites are like this. We have, depending on the modal abundance of the ferromagnesian silicates, we have spotted, leopard type, then screen banded, massive character, stratified character, different types of chromatites within these ore bodies. So this is the character of the breccia zone, where ultramafic and chromitite cluster cemented by pegmatitic gabbro, which is at the contact part of this chromitite or ultramafic class. We have sulfide mineralization, and those are PGA rich. This is the gabbro at the eastern part, and these are the magnetite. In the complex, we have 6 thick chromitite layers, which are like from west to east. We have orthopyroxenite unit at the westernmost part. Sometimes this orthopyroxenite gets to Hajbargite, like Noamundi igneous complex. Then there is another orthopyroxenite running here, and there's a folded as a whole. The whole complex is folded, and these massive chromitite bodies, along with the host rocks, are capped by a thick laterite unit, which is nearly 40-meter thick. So the whole complex is extensively weathered, lateritized, and you have a similar kind of breccia zone at the southwestern part of the complex, where there are some disseminated sulfides and platinum group minerals already reported, but the Pg concentration is not so much significant like the Noamundi igneous complex. So these are the field photographs of Shukhinda chromite deposits. You can see the nature of the host rock as well as chromitite bodies. Sometimes this chromitite, they show pinch and swelling character and extensively weathered and deformed. And however, sometimes within some chromitite bodies, we can find this kind of primary layering. And in some serpentinized dunite, we have some residual olivine. So those are the minerals we can analyze. And most of the ancient deposits in India, like the host rock is extensively altered, and chromite is also very much altered. So it is a real challenge to find the parental magma composition, to understand the petrogenesis of the igneous complex, along with the origin of the chromitite bodies. So this is the geological map of Craton. We have Western Craton, and another part is Eastern Craton. In Western Craton, we have similar kind of early Archean to Mesoarchean greenstone belts, where in association with these greenstone belts, metavolcanic meta-sedimentary rocks, we have plutonic pseudo rocks, such as in Sargu greenstone belt, and also in the Nugihali greenstone belt, we have this kind of chromitites, which are elliptical in shape, sometimes pot shape. They're discordant to concordant bodies present within serpentinite, extensively serpentinized dunite pyrrhotite rocks. They're deformed as well. And if you see the chemistry of these chromites, in case of Noamundi and Shukhinda complexes, I have just here I'm basically giving some ideas about the composition of the unaltered chromite from massive chromitites. We have analyzed chromites from accessory chromites from all the silicate lithium units and altered chromites and everything we have, altered chromites from the breccia zone of Noamundi and Shukhinda, but these are basically representing the unaltered chromites from the massive chromitite units. So the idea is that we can use we have to use composition of the primary chromites to understand the tectonic setting and to calculate the parental magma. So that is the reason basically I'm showing this unaltered chromites here. So in terms of CR number and MG number, they are characterized by high CR number and MG number, and they show the resemblance with Selupe chromites of Zimbabwe. We have some chromites in stillwater chromitite, G-chromitite composition here, and you can see the difference between the composition. And if we plot this composition in AP3 plus CRAL triangular diagram, these chromites from Noamundi and Shukhinda, they show resemblance with the chromites from boninites or chromites from komatiites. And there is a discrimination plot proposed by Kamenetsky based on chromite and melt inclusion studies of volcanic system. And in terms of TiO2 versus Al2-3 plot, there are definite fields for different tectonic setting. And these Noachahi and Shukinda chromites show resemblance with the R-derived magmas. And this one is another similar kind of plot. We have um, chromite compositions which are coming from chromatites, chromite compositions which are coming from boninites and mid-ocean basalt. And we have ophiolitic chromatites here, and our Noachahi and Shukinda, along with Seleucid chromites, they are showing a resemblance with the chromites from the boninitic magma. So we have some kind of mechanism to calculate the parental melt because we are talking about cumulate rocks. So the cumulate rocks from Bushveld complex, we can understand their evolutionary path by means of field studies and other mechanisms, because those rocks are not altered. And so we have primary minerals over there. The main problem with this Archean ancient deposits is that there are very little scope to analyze the host rock. At the same time, those are extensively altered and recalibrated as well. So the primary composition of chromite can be taken out from the massive chromitite unit, because the reason is that those chromites are less altered, and they should preserve their original composition, crystallization compositions, and liquidous compositions. So using different experimental relations, like as proposed by Morel and Morel, it is based on the formulation is constructed on the inference that Al23 in the melt. So we can use this equation. Then there are other relations, like to determine FU by MgO ratio. So FU Mg ratio of the magma from the primary composition of the chromite. So we have conducted many such calculations from the primary composition of the chromites from Noachahi and Shukinda, and we have found that the composition of the parental melt probably was a high magnesium siliceous basalt or boninitic magma or low alumina chromatic magma. We did the same thing for Nuggihali and Sargur belt, and the parental magma composition in those belts, for those belts also giving a composition similar to boninitic magma or high Mg siliceous basaltic magma or low alumina chromatic magma. We have conducted some osmium isotopic studies of these chromatites from Noachahi and Shukinda, these primary chromites from Noachahi and Shukinda. And chromites from chromatites have very unradiogenic osmium isotopic ratios. There is no sign of crustal contamination or anything in these chromites. And initial gamma osmium values of chromites from chromatites are consistently negative, indicating derivation from a subquantity source. And osmium isotopic study indicates melt extraction as early as 3.7 billion years ago from a subquantity osmium isotopic source, and that implies derivation from a subcontinental lithospheric mantle. So we have conducted many more studies based on silicate mineral inclusions in chromites from Nuggihali, from Noachahi and Shukinda, from Sargur. And in case of Noachahi and Shukinda, you can see here that we have most of the primary inclusions are chrome dioxide along with phlogopite. And we have analyzed plenty of grains using electron probe microanalysis for major element compositions. And we have analyzed this clinopyroxene using laser ablation as PMS. And this is the composition for clinopyroxene. It shows relatively higher chromium concentration. It is unlike the clinopyroxene we have in Gabbro, or also compared with the clinopyroxene from the footwall of UG2 pyroxenite or Bushveld complex. So major and trace element composition for clinopyroxene inclusions are like the mantle clinopyroxene, is a composition of chrome dioxide, and phlogopite is potassium rich in case of Noachahi Shukinda as well as Sargur belt. And they're also like mantle phlogopite. And from this observation and other data, we propose that high magnesium parental magma may have originated in a metasomatized lithospheric mantle was from where the clinopyroxene and genophyst were collected and entrapped by the chromite crystals from the magma. So there are some data on platinum group element mineral inclusions on these chromites. And in case of Noamundi and Shukinda massive chromatites, it shows that these inclusions are osmium, iridium, ruthenium alloys. 90% of inclusions are osmium-rich iridium, ruthenium alloys. And we propose that these inclusions, perhaps within the chromatites, may begin to nucleate in mantle at high temperature and low sulfur fugacity condition, because these are mostly alloys. We don't have much sulfide inclusions in chromatites. And it was carrying by the magma when chromite crystallizes and entrap these IPG alloys. So melting of a metasomatized subcontinental refractory mantle was, which was lithospheric, subcontinental lithospheric mantle, accompanied by fluids derived from the downgoing oceanic lithosphere, would account for these IPG alloys in chromites and overall IPG-rich character of the chromatites from the Shukinda massive. So we propose this model based on not only based on these alloy inclusions in chromitite. Most of the cases, these chromatites are IPG rich, and the similar things like we have found for Nakihari and Sargu belts, and these are showing. These are also characterized by high CR number and high magnesium number. And in terms of the parental magma composition and other tectonic discrimination plots, we have found similar kind of things, like these are basically low aluminum, chromatiite to bonanite to high magnesium, siliceous magma perhaps. And we propose similar kind of mechanisms for this kind of magma generation. So in summary, because we have relied on liquidous chromite composition plots, and we have calculated the composition, parental magma compositions from the primary chromites, and everything suggests evolution of these rocks, including chromatites, from a low titanium, high magnesium siliceous magma or bonanitic magma, or a low alumina chromatitic magma. And parental high magnesium magma may be genetically linked with the with specially associated chromite bearing high magnesium basaltic magma, chromatitic basaltic magma that present in the extrusive system, which we have within the greenstone terrain. And combination of magma mixing involving the high magnesium magma, bonanitic magma, and relatively high water contents in magmas derived from upper mantle in a suprasubduction setting can best explain the origin of chromatites in the Shinghum and Western Tharwar Cratons.